Welcome to DockerCon 2021. Thanks so much for joining me. I actually attended DockerCon 2016 in Seattle in person, remember the before times, as an attendee, so it's really an honor to have the chance to present to you in 2021. I hope you're staying healthy and sane wherever you are. It's been a really very different and tough year for many people. My name's Julian Wood and I'm a Senior Developer Advocate here at AWS Serverless, certainly now with more lockdown hair than my profile picture shows. I work as part of a team within the wider serverless organization at AWS, and we teach and educate builders and developers to help them understand how best to build serverless applications, as well as being their voices internally to make sure we're building the best serverless products and features. Prior to this, I was an infrastructure engineer, architect, and a manager for many years and worked in large global enterprises and some startups. Please feel free to contact me anytime with your serverless questions, whether you have questions from today or other general questions around serverless development. Today, I'm going to be talking about a really awesome new capability for AWS Lambda, which is one of our serverless compute offerings here at AWS. For those of you that are new to AWS Lambda, it's a service that first announced more than 6 years ago now, back in 2014, and it's grown since then to become an incredibly popular service with our customers, and we see customers doing all sorts of unique things with Lambda. Many of our builders and customers have made big investments in container tooling, development workflows, and expertise, and as they start to modernize existing applications or even build new ones. But you and likely your development teams in your organizations have found it difficult to leverage your container investments and know-how when building Lambda-based applications. And so to help with this, Lambda now enables customers to package and deploy functions as container images, and I'll be covering what that all means. But first, let's take a step back and just talk about what serverless application is in general from the perspective of Lambda. From a high level, which is actually a pretty simple idea, a Lambda serverless application is event-driven and composed of three things. An event source, this is something happening. It can be a file uploaded or a database record updated or something appearing in a queue. A request hitting an HTTP API endpoint can be an event or some change in a resource. And this event triggers a function, which is basically a compute service, a little piece of code, and this triggers a Lambda function. And at AWS, it's our foundational serverless compute service called Lambda. It's made up of code that you've written, which is your business logic in your application to react to whatever the event is. And this function can be written in one of 6 what we call runtimes, and that's supporting various languages. And you can even build your own custom runtimes to bring pretty much any language to Lambda. And people have built things using PHP, Rust, Scala, even COBOL. The function can then go and perform whatever it needs to do. This could be update a database record, return something to a client, talk to another API or endpoint that exists somewhere, send its output to another service. Lambda again is a compute service, so it itself is running on top of underlying compute resources. Yes, there actually are servers in serverless, but again, you don't have to think about them, you don't have to manage them, you don't have to scale them yourself or pay for idle for them or deal with high availability. A Lambda function itself is just some code, and this code has a handler function, which is the main entry point into your function code. This is the business logic of the code that you've written. There's an event object, which is the event that triggers the Lambda function, and this is the data that you want to send to your Lambda function to do that business processing on. And then there's the context object, which provides methods and properties that gives information about the invocation, about the function, and the general environment. So previously, Lambda functions were packaged and stored only as zip archives. So I'm going to talk about the new Lambda container image functionality. I'm going to start with why you may want to consider Lambda, particularly if you come from a container world, and also go through the benefits of this new container image support. I'll show how to build and work with Lambda container images and go through some of the developer workflow, and then do a bit of a level set and show what does changes with this new functionality and also what stays the same with the rest of how Lambda works. So development teams that currently use containers may ask the relevant question, why Lambda? Well, as a compute option, Lambda has several interesting and unique characteristics. First, Lambda is the general compute option that provides the greatest level of operational support by AWS. And this means it's been designed to simplify the implementation of high availability, scale, and security within an application. AWS has many compute services across a spectrum of operational support models, and you can start at the very bottom with EC2, our VMs in the cloud, and have access to all the knobs you want to manage, or you could go completely serverless with Lambda, where you're focusing most of your efforts on your business logic. And so teams who want to shift the greatest amount of undifferentiated heavy lifting to AWS often start with Lambda. We often talk about the AWS shared responsibility model. With our managed container services, what you manage on your behalf, what we manage on your behalf, and what you manage. And you can see here, if you're using managed containers, there's sort of a divide at the OS and network config level of the stack, where you take on the responsibility of managing your infrastructure and applications. But when you use Lambda, we take on even more of the operational aspect, and you get more time to focus on your application components. And let us look after more of the infrastructure for you. Another major differentiator for Lambda is its integrations with other services. Lambda has native integrations with over 140 other AWS services without you having to manage any code or applications to run these integrations. And these built-in integrations also provide a wide range of conveniences in how you can interact with these services. And these include things built into the service like polling and batching and queuing, event routing, retries, etc. And you get these features for free with Lambda, and they can add maturity to applications built using Lambda as the compute option in an event-driven architecture. Lambda also has unique auto-scaling characteristics. One of the most interesting aspects is how it can auto-scale with its burst capability, where Lambda can scale from 0 to 3,000 concurrent executions immediately within seconds. After the initial burst, you can then scale by another 500 concurrent instances every single minute. So if you have unpredictable on-demand workloads that can benefit from rapid scaling, Lambda is a really good choice. And Lambda also provides a feature called provision concurrency. So if your workload demands can be planned ahead, you can automatically build up that concurrency in advance of when you need it. Lambda's billing model is also unique. With Lambda, you never pay for idle resources, since Lambda only charges you for what you use and scales to 0 when it's not needed. In December of 2020, we increased the precision of Lambda billing from 100 milliseconds increments down to 1 millisecond. And we've had many customers who saw their Lambda bill drop by more than 30 or 40% when we did this. And you can manage the cost and performance of your function by allocating memory to your function, which also adds proportional CPU. And of course, with Lambda, you can avoid paying the human costs of patching and maintaining servers. So let's look at some of the benefits of packaging your Lambda functions as container images. Lambda container image support enables you to pair the flexibility and familiarity of your container tooling. And these are things like including the Docker and container-based CI/CD workloads, and maybe some security and governance tools, along with the operational simplicity of Lambda. And this is to give you greater agility when building your applications. One of the common challenges customers have found with managing the lifecycle of Lambda functions, as well as managing how they install software in their Lambda environments. And with Lambda in the past, it hasn't necessarily always been the simplest process to do that. Here, of course, there were some tools and ways you could import code, but this really could have been simplified. So now with this new feature, Dependency Management now works like it does with other container systems. You build an immutable artifact from a Docker file where you manage all your dependencies, and you can use your package manager of choice. So you can use your npm package or pip install, or for Java, there's Maven. For .NET, there's NuGet, and Ruby has gems, and so forth. You get the idea. And you can install native operating system packages as you could do with any other Linux distro, things like low-level code libraries or full applications. And now you can build your images exactly as you like them, and can be sure that the software runs as you expect from your laptop all the way through to production. And you get also to use your familiar and favorite container tooling that you've already been using if you've been building container-based applications. And now you can share that same tooling with Lambda, and this could include tools like the Docker CLI, as I said, the same build and CI/CD pipelines, and use that for Lambda. You can also store your Lambda application artifacts in the same registries as your other container artifacts. And also this allows you to use your native container security scanning and maybe other governance tools that you already have in your container world. And now you can use this to build Lambda applications. You'll definitely benefit from the option to run larger workloads on Lambda, and Lambda has recently increased several limits. With zip archive functions, the limit is still 250 meg, but the deployment package limit is now 10 gig for container images. And so now you can run a Lambda function also with up to 10 gig of memory and 6 virtual CPUs. And the memory and the CPU ratio is also available for zip archive functions. So these changes really make Lambda a great choice for data-heavy or dependency-heavy applications, maybe like AI, ML, or some data analytics. And those of you who work with Python libraries like PyTorch or TensorFlow or other data science or libraries, these can be pretty big. Models for machine learning, and maybe you've been prevented from deploying to Lambda by the 250 meg limit. Well, this is for you. Lambda can now be a great option for those larger workloads. Another benefit is immutability, which I touched on before. So Lambda treats container images as immutable entities. When invoked, functions deployed as container images are run as they are. So you can feel confident that your functions are immutable across a number of different environments, such as your desktop or laptop, your CI/CD pipeline, the Elastic Container Registry, which I'll cover, and then eventually when it runs in the Lambda execution environment. But with this immutability does come some more responsibility. The OS and runtime patching are no longer performed by AWS, and so you won't benefit from pre-0-day patching if that's applicable. Any changes to the image does require a separate redeployment step, which you need to add now into your operational procedures. Because you own that runtime and you own the container image, you no longer get the automatic updates to the runtime. And this is an important caveat for the service, as it's something that's from the early days of Lambda was a real benefit. We would manage all the updating for you with zip archive functions, and we take ownership of the runtime so that you just consume it. That's not always ideal. So if you have an example that's maybe very tied to a specific release of a runtime, or you have certain dependencies that you use which aren't forward compatible, when we update the runtime, that could break your function, and that has happened for some customers. So with container image support, you then can take on the ownership of updating that runtime. So when there are performance fixes, security or bug fixes, or new runtime versions, that's now on you to then update these container images, and you can create a new version of your function and build from the latest build image and then pass on that new function through your testing pipeline. And then you can make really sure that any updates don't cause anything you don't want to happen before moving it into production. So it's important to understand that bit, which is a pretty fundamental shift with the contract that Lambda provides for you. You certainly get more flexibility, and you can now use your preferred Linux-based images, which you may be using elsewhere, to now deploy Lambda-based applications. Lambda has a runtime interface emulator, which I'll describe shortly, that simplifies running images locally and on additional compute services. And those other compute services give you some increased portability. So you can create Lambda functions that you could also run in other places, such as AWS Fargate or Amazon EC2, or on premises or in hybrid cloud environment. So, this isn't running like the whole of Lambda with all its integrations, scale and availability, but it does mean your actual function code can be used elsewhere. So how does all of this work? Well, Lambda supports the Docker image manifest schema and the OCI spec. And as I mentioned, you can use your Amazon Linux distros to build, you can use non-Amazon Linux distros to build your applications, which can be up to 10 gig in size. So previously with zip archive functions, you needed to use Amazon Linux or Amazon Linux 2, which are our own long-term supported Linux distros. Now, Lambda supports all Linux distributions, so you can build your functions maybe off of Alpine, Debian, and Ubuntu, or whatever you want. Lambda supports container image deployments currently from the Amazon Elastic Container Registry, or ECR. And yeah, of course, we're looking at and gathering feedback on perhaps supporting some other container registries. Now, ECR is a fully managed container registry. It sort of works conceptually in a similar way to Docker Hub. It has public and private registries. You can share your images across accounts and publicly, and also automatically replicate them across regions as part of the service. And there's some great security controls with encryption at rest and in motion. And Lambda ECR also has integrated vulnerability scanning. So let me talk about base images. So as part of the feature, Lambda provides a variety of curated container base images for each runtime. So this allows you to very easily take your existing code for Lambda and combine it with a container image for the language that the code's programmed for. And these base images are patched and maintained by AWS when you build your image, which you can then use. So you can see the available images for supported runtimes there, as well as an image for the runtime API, so you can bring any language to Lambda. And you can easily get these base images. They're available from Docker Hub and Amazon ECR Public. And as I mentioned, you can now provide your own base images rather than the default Amazon Linux-based ones. And you can also use Docker's multi-stage builds to manage the content of your images. So looking in a bit more detail at what a Docker file for a Lambda function looks like. This is a very bare bones example, which just has 4 lines. And it's going to use the Node.js version 12 base image, which is going to pull from Amazon ECR Public. And as this is a managed runtime using our image, in which we pre-bake a whole bunch of stuff into that, which makes it super easy to run your Lambda function. The function's application code is now in app.js, and that file, along with the package.json, which is where all the dependencies for this function are defined. And then you can run within your Docker file a standard node npm install, and this runs, which adds all the dependencies in the image from that package.json. And then when this image runs, the CMD line points to the file and the application's handler function, and this is the code Lambda runs during an invocation. So the container image artifact includes your function code plus all the dependencies, and the image becomes the entire file system. You can specify the container image settings in the Docker file when you build your image, and Lambda supports the following settings: entry point, CMD, workdir, and env. You can actually also override these configurations using the Lambda console or Lambda API. So you could maybe deploy multiple functions using the same container image, but with different runtime configurations. Lambda does actually ignore the values of any other container image settings in the Docker file that aren't supported. So remember, Lambda works in an event-driven model where functions are invoked based on an event. And this is rather than a port and socket model, which you may be used to with other container runtimes. Part of Lambda container image support brings 2 new open source components, the RIC and the RE. RICs, which stands for the Runtime Interface Clients, are wrappers that act as a shim to integrate your function code with the Lambda API at runtime. This is how you can connect to the Lambda service. So RICs are pre-installed, as I said before, on the AWS vendor base images, or you can download the RICs and install them on your custom base images. They are open source and available via language package managers such as npm and pip. The RE is the Runtime Interface Emulator, and this is a small application that acts sort of like a little web server inside your container, and you can use it to emulate the Lambda service, and this is great for testing your function locally or running your Lambda function in other environments, as I showed before. And how the emulator works is it listens for HTTP requests on a port inside the container. It then wraps those requests as events and then serves them onto your function. And as well, the emulator is open source and available for download. So let's now look at the workflow to get your code into a container image and running in Lambda. You start by writing the code for your Lambda function using your whatever IDE of choice, and then you write a standard Docker file, which I showed. And this pulls the base image you want. It then copies the function code and installs any dependencies. You then use Docker build, the normal Docker build, to create the function image. And again, you can use Docker's multi-stage builds to squash unnecessary layers in your final image, which is super useful for removing build steps. You can then test this function using the local image, and you can use Docker run with the runtime interface emulator, the RE, and you invoke your local function and pass it an event and monitor the output. And this is the easiest way to quickly iterate on your code. This local function can also interact with other cloud resources, so you don't have to locally mock all the other AWS services. And this gives you the best of both worlds. You can quickly iterate on local development and also use the depth and breadth of cloud resources. AWS Sam is our serverless specific infrastructure as code framework, and this makes it even easier to build serverless applications. And you can actually use Sam build for the build process and then Sam local invoke for the testing. And you can use it here to test Lambda functions, but you can also use it to mock API Gateway if you need to. API Gateway is our managed API service. So you can really easily iterate on your applications locally. And it's pretty powerful AWS Sam and certainly worth taking a look at. So once you're happy with the build of your container image artifact, you tag and you upload it to ECR, typically by using Docker push. And then next you create your Lambda function. This is either in the console or with the AWS CLI or any available function create tool. And the Lambda service then creates the function, sets the status to pending, and then Lambda then pulls the image from ECR and optimizes it. And when the optimization process is complete, the Lambda function enters the active state and is all ready for invokes. And just the optimization phase also involves Lambda securely chunking and caching the image within the service. And it does this near to where the function runs. And this really improves function startup performance, particularly for cold starts. So if you used AWS SAM build before to package the container image, you can now use SAM deploy also, which automates even more of the steps. SAM deploy will tag and push the image to a repo and creates or updates the Lambda function with a single command. Super easy. So I've talked a lot about the new functionality, so it's worth level setting to see what changes and what changes and what stays the same. The main new change are the larger function sizes up to 10 gig and being able to use your own Linux-based images with the RIC to talk to the Lambda service and using the RE for local testing and portability. And then I spoke about immutability, which is helpful, but does mean you need to manage the updates to your functions. But a lot of Lambda also stays the same. Container image support is a packaging format option. A lot of Lambda still works in exactly the same way as before. This includes the operational and invoke model. You're still limited to 15 minutes of maximum function duration. The burst limits and the account limits are still the same. And you know how the performance works and there's storage behind the scenes and observability and limits and pricing. These all stay the same and I'll go through some of them. So first thing to mention, that's the same as performance. Memory and CPU configurations for container images match the larger function options I went through previously. Now, of course, the performance of any Lambda function is going to be based on, the image size, how it's built, the runtimes and any dependencies, and there are great resources to help you with optimizing this. And cold start times, which generally only impact a very small percentage of production traffic, are targeted to be the same as zip archive functions. And this is due to the way I said how we cache the potentially larger images close to where the function runs. Pricing is the same for Lambda. We now build at 1 millisecond granularity, reduced from the 100 milliseconds at the end of last year. With container images, there's no additional Lambda pricing changes or dimensions, but you do need to pay some for image storage in the ECR repository. And importantly, the Lambda resource and operational models are exactly the same for container images. And this includes the auto-scaling characteristics, the same burst mode I spoke about. High availability is the same, including by Lambda working by default across multiple availability zones. And the security model as well as isolation are the same. Actually, while we're talking about Lambda function isolation, Lambda runs functions on what we call Lambda worker nodes, which are bare metal EC2 instances. We then use a hardware virtualization technology called Firecracker, and this uses Linux KVM to create lightweight and fast-starting micro VMs, which we call execution environments, and we use these to isolate the functions. So we're not actually using Docker containers for the function isolation. It's at a micro VM level. Execution environments, they're never shared across function versions or customers, so it's incredibly secure, and memory and disk state isn't accessed or shared across execution environments either. And then each execution environment gets its own secure writable temp folder. So talking more about storage, internal to the Lambda function, depending on how you configure it, you have between 128 meg and 10 gig of memory available. Every function includes a writable temp storage space. This is always available and a maximum size of 512 meg. And this is separate from the deployment package size. That's read-only and up to 10 gig. For persistent storage of data external to your function, you've got two primary options. The first is S3, allowing you to store data as objects in buckets. And you can also use Amazon EFS, an elastic file system, basically NFS in the cloud. And of course, you can use persist information in databases or other non-storage places external to your function. After your invocation finishes, the execution environment is destroyed at some point after, deleting all the memory and internal temporary storage space. So we now have 3 different models to create and package your functions. You can still use the Lambda console, you can still use the zip archive method, and now we've added container image support, which brings even more flexibility and size to build and run Lambda functions. So to summarize, container image support gives you some more options and can simplify the way you build Lambda-based applications. You can use your existing and Docker-based tooling. There's easy dependency management with a larger artifact size, 10 gig. This really allows you to combine the flexibility and familiarity of your container tooling with the great operational simplicity of Lambda, giving you greater agility and really a simplified developer experience when building your applications. Certainly worth trying out AWS Sam too, or having a look. That really makes things even easier. So there's much more information and more blogs, videos, and other material to digest specifically about this topic via the link and the QR code provided. For plenty more information on all things serverless, we have a super aggregation site we maintain called serverlessland.com. And this has got lots of resources, blogs, workshops, videos, and learning paths. It's really everything about serverless on AWS. So thank you. I really appreciate you taking the time to watch today and hope I was able to help you understand how you can now build Lambda functions as container images. My name is Julian Wood, and you can find me on Twitter at Julian_Wood.